All right, okay. So like I mentioned, we're going to start chapter 6 here. This is the last chapter for the analytical portion of this class. It says linear and nonlinear maps, and honestly, we're only going to do nonlinear maps, so I should just say nonlinear maps. In fact, I'll fix that right now. You can study linear maps. We are just not going to, just due to time. Okay, so a map is a discrete dynamical system and usually defined as X is a mapping or evolves from some function g of X with some parameters. We'll use mu here, or in other words, xn plus 1 is equal to g evaluated at xn with parameters mu. Where X is at the least on some subset of the real numbers. It could be multi-dimensional maps. We're only going to look at one-dimensional maps, but these ideas can be expanded on towards multi-dimensional maps. So discrete dynamical systems are a class of dynamical systems that are totally different than vector fields, which are continuous. And so the idea of what a dynamical system is not the same as what a continuous vector field is. Those are independent concepts. And that being said, when we're talking about discrete dynamical systems, we're thinking about something discrete in time happening at certain points in time, at exact points in time. We're not just thinking about like you've taken a continuous system, sampled it. We're not thinking about that. We're talking about systems that only exist at these discrete iterations or discrete points in time. And generally, you can extract a discrete dynamical system from a continuous dynamical system. For nonlinear systems, the construction of Poincare section or Poincare maps, which we'll do on Thursday, is an example of this. For linear systems, you can use a method called the eigenrealization algorithm to construct discrete dynamical systems from continuously measured sampled signals of continuous systems. So you can construct these discrete things from continuous systems. Okay, so additionally, maps tend to represent the lowest dimensional systems that can exhibit chaos. We'll see chaos pop up today. There are two types of maps that can exist. The first are those that are invertible. And then the second are simply those that are non-invertible. Invertible meaning you can take the inverse of the mapping, and then you could, in theory, if you wanted, you could go backwards in time. Non-invertible meaning you can only go forwards in time. You can't take an inverse. Okay, so kind of a formal definition here. The map G of X with parameters mu is some CR diffeomorphism if G is invertible with an inverse denoted by G to the minus 1, and both G and G inverse are CR maps, meaning that they are to the rth order differentiable continuously. And if you've never heard this word diffeomorphism, it's just an invertible function that maps one differentiable manifold to another such that the function and its inverse are both differentiable. Okay. You can also study homeomorphisms, but we're just going to skip that. So our real goal here is to study what are known as the orbits of the map 1, and equation 1 is up here. We want to study what we call orbits in this, or periodic solutions. Okay, so for an invertible map, orbits are going to be bi-infinite sequences of points, and we're going to write out what this sequence will be. So we're thinking about, since it's invertible, we can go both forwards and backwards in time. So over here, we're going to have g to the minus n of x0 mu, where here x0 is our initial condition, comma dot dot dot. Then we'll have g inverse x0 mu, comma x0, and that's our initial condition right there. So x0 is our initial condition. Then moving forward, we'll have g of x0 with the parameters mu, dot, 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 here, then g n x0 mu, so on. So it's a sequence of points at discrete times, which you could decide to give those times specific labels, or you can just use the counting numbers, natural numbers. Okay, so again, x0 is generally in subset of the real numbers. For some maps, they may not be defined for the entire real number set, and that's why you end up defining them for a subset. Okay, and then g n here of x0 with the parameters mu, this is equal to g applied to g n minus 1 x0 mu again. Valid for n greater or equal than 2. So here, the notation g with a power of n is not an exponent. It is, it's an iteration, an nth order iteration of that initial condition. And the same thing with the inverse. When we have g to the minus n of x0 mu, this is equal to g, the inverse of g applied to the minus n plus 1 iteration. And then, like I said, n represents the iteration here. It's not an exponent. So we're not thinking powers of g, we're thinking iterations of g. So again, for an invertible map, if we're given some initial condition, we could go backwards in time and compute the paths that led up to that initial condition. Okay, so for non-invertible maps, then, we will end up with a semi-infinite sequence of points. So in this case, we're going to start at some x0, and it's non-invertible, so we cannot go backwards in time. And then we'll compute g of x0 mu, the second iterate, and so on until we get to the nth iterate of x0, still with the parameters mu. If you haven't seen it before, that semicolon inside the parentheses just means that everything follows is parameters. And we're just storing all of the parameters into whatever variable you put there. So that mu might be a single parameter, or it might be a whole list of parameters in this notation. So what we want to do then is look for fixed or equilibrium points of a map. And for x being in that subset U, we can define the equilibrium point to be that g of xe for our equilibrium point. We have an x over bar here. Let's change that to an xe. The notes I were following had x bar, but we've been using bar for complex conjugates, so I wanted to not use that. If there's an x bar anywhere, you let me know. I think that's the only one that should be in the notes. If not, let me know, and then we can correct it. So we'll use x sub e instead. So g of x sub e should be equal to xe. So you input xe and you get back xe. And that's how you know it's stable, or that's how you know it's a fixed point at least. Whether or not it's stable, that's something we're going to determine, but that makes it a fixed point. Or in another notation, you can say that x is mapped from g of xe and I drop the parameter here. Okay, so just so we can be clear, we don't want to mix concepts of equilibrium points or fixed points from vector fields with those of fixed points from maps. In fact, we don't want to mix concepts from vector fields with concepts from maps. These are separate, but they're still dynamical systems, but there's separate and different types of dynamical systems. So just as a recap, for a vector field, we said that x dot was equal to some function f of x, and this was continuous in time. And then x here, in this case, lives in the real numbers Rn. And then to find the equilibrium points, we would set, or the fixed points, x dot equal to 0. From there, you end up finding that f of xe is equal to 0. And then if you can inverse that f, you can then find the equilibrium points. And if you can't do that analytically, then you end up doing it numerically. For maps, we say that x is mapped from g of x, or xn plus 1 is equal to g of xn. Here, x is in some subset, at least some subset of real numbers. It could be real numbers, the whole real numbers. Generally, it's some subset. In this case, the equilibrium points are mapped from the function or the map itself being evaluated at the fixed point, or such that xe is equal to g of xe. So everything we've done previously was all done with vector fields, and a lot of work is done with vector fields in general, but dynamical systems are independent from vector fields. Vector fields are just a subcategory of dynamical systems. Okay, an interesting thing with maps is that you can have equilibrium points that have multiple periods. So, for example, if we have an equilibrium point xe1 that is mapped from g applied to xe2, which is mapped from g applied to xe1, you can say, rewrite this as xe1 is mapped from g, second iterate of g, or g squared, xe1 here. And we can call this a non-trivial period 2 orbit, or fixed points, I guess. And we're going to see in a couple pages where this pops up and how you actually do get a period 2 point. Likewise, if you have an equilibrium point xek, and this is mapped from gk of xek, then this becomes a non-trivial period k orbit. All right, so on the next page we're going to do an example, and we'll start to study these things in more detail, or with an example at least. Okay, so then a period k fixed point of a map is defined as another x bar here. Is defined for that fixed point being within the subset that the map lives in, such that gk of xe is equal to xe, and again xe here is mapped from g to the k xe. And that is here that we have G applied to G applied to dot 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 G of XE. And that is all equal to XE. And again, this is where we get our K iterations. Okay, any questions before we do an example? Okay. Let us then take a look at the quadratic map. In this case, this is going to be X, so let's change the color. We'll have X, n plus 1 is equal to alpha times xn times 1 minus xn. And in this case, we have G is some function of xn with the parameter. In this case, alpha is our only parameter. And using the other notation, you can say that x is mapped from alpha times x times 1 minus x. And note that this map actually comes from a model for population dynamics where the discrete time represents years typically, although you could change it to something else. And it's called the logistics map. There are several different forms of the logistics map, and you can show that, just as an aside, you can show that they will all end up having the form of something like alpha minus x squared. You can do a coordinate transformation to go from what we've written up here to something like this equation that I just wrote down. Nevertheless, this is a map used to define and determine how the population of a species will evolve over several periods of years. And then depending on the kind of alpha you choose, you can have various different types of fixed points, meaning you might have a stable population that stays at the same amount forever, or it might oscillate between different levels of population. Let's take a look. All right, so we're going to compute the fixed points by solving the following equation, which is that XE should be equal to alpha XE times 1 minus XE. We could just bring that XE over. From here, we can actually factor out an XE. We get XE multiplied by square bracket alpha times 1 minus XE, close the parentheses, minus 1. All that's equal to 0. So right off the bat, we'll find that XE equal to 0 is one fixed point for this map. If we take what's inside of the square brackets, we get alpha times 1 minus XE minus 1 equal to 0. From there, we get 1 minus XE is equal to 1 over alpha. From there, XE is equal to 1 minus 1 over alpha, which is also equal to alpha minus 1 over alpha. And then therefore, we find here that the fixed points are either XE equals 0 or XE is equal to alpha minus 1 over alpha. I'll give everyone a moment to catch up, and then I'm going to show a plot of this map for alpha less than 1. And then we'll choose some initial conditions, and we will do some actual iterations on the map. All right. I'll zoom out a little bit. So what I've shown here is in black we have a coordinate system, and we'll add some here. So on the x-axis you have xn, on the y-axis you have xn plus 1, the n is plus 1. I'm not going to write that for all the axes, but that's what we're plotting here. This red curve is our map, the alpha x times 1 minus x, and the blue line shows us where fixed points end up. It's a 45-degree or x equals x line, and wherever our map intersects this line, that is where we have fixed points in this case. So unlike a vector field where you have where you can study fixed points as intersections with 0, in this case we're looking at where do they intersect this 45-degree line. All right, so I've labeled here that for alpha less than 1, the x equals 0 fixed point is stable, and we can show that by picking an initial condition right here. Given that initial condition, the next iterate is just going to be straight on up. From here, what we do is we'll draw a horizontal line from that value to the 45-degree line. Then we'll draw a line down, and that takes us to now the third iterate. And then we'll continue and go horizontal to the 45-degree line, then down vertical. And then as you can see, we are iterating towards that fixed point. If we pick an initial condition, let's say over here to the far left, we'll again draw a vertical line down to the curve. That is our second iterate. We then draw a horizontal line to the 45-degree line, and then vertical down, and I've already gone off the page. And continuing, we will iterate away from that point. Let's pick another initial condition to the left here, but to the right of the xe equal to alpha minus 1 over alpha, but still in the negatives. Again, we can draw a vertical line to get to the first iterate. From there, we draw horizontal to the 45-degree line, and vertical, horizontal, vertical, and so forth. And we end up iterating towards x equals 0 as our fixed point. Okay, so that's for alpha less than 1. When we go to alpha greater than 1 but less than 3, what ends up happening is the stability of the two fixed point switches in this case. And that is actually because the slope at them is now changing, and specifically at xe equals 0, the slope is now greater than 1, and as a result, the points will grow away from it. In this particular plot, the slope at the right fixed point is practically 0, but in this range is somewhere between -1 and 1. And the key thing is that when the slope is larger than 1, when the absolute value of the slope is larger than 1, that's when the fixed point becomes unstable. And again, we can show this by choosing some initial conditions. We'll choose one right here. Pick one right here. If we go, just draw a point. Okay, we'll just go straight down. Hit right here, again here, go horizontal and then vertical, and we're off the page, and we're going to iterate away from that fixed point. If we choose initial condition inside somewhere here, the first iterate takes us onto the curve, the second one takes us to the 45-degree line, and then up vertical onto this point, and if we continue, we're going to end up at that right fixed point. Same thing, if we choose one on the left, we can go up, and then horizontal here, vertical up. And so here we've crossed on over to the other side of that 45-degree line. And as a result, we'll have to go to the right here and then go up vertically, and we're almost practically at the fixed point. So in this case, we can actually show the stability just by doing a few iterations on these points and so forth.
So this the dashed blue line is not necessarily to be 45. It's just a connection between the two stable, like the two fixed points.
So no, actually, well, both are correct. So it's not necessarily 45 on this plot because it's not perfect aspect ratio. However, it is a 1-to-1 between the two between the vertical and the horizontal mapping. So it is the x equals x axis. Okay. So it's a 45-degree, and all fixed points occur at the intersections of this blue line. So it is also a line that connects the fixed points, but that's because the fixed points are defined by being an intersection of this blue line. So
is it a coincidence, or is it like...
It's a consequence of the definition of a fixed point, is the thing. So the blue line exists regardless of what you decided for fixed points, but I mean, we don't really necessarily get to choose the definition, where you can. But, you know, if we're thinking about a population, if the population stays the same every year for many years, then we would consider that to be a fixed population, and therefore a fixed point. And that's really where this stuff evolved out of, studying population dynamics, which is usually why people start by talking about a quadratic map or a logistics map. And as a result of that, that's where this 45-degree line comes from.
Is this line happening just for the logistic map, or are we going to see this 45 with every other map?
For every map. For every map. Because this is always the definition of a fixed point. In the next figure, we're about to see where the fixed points actually do not intersect this line. But we'll do some more work and show where it will intersect again. Okay, so if we go to alpha equals 3, we will end up finding that both fixed points become unstable. And we can show this with a few different iterations or initial conditions. Let me move this to layer 2. If we choose a point here, let me go a little bit closer to 0. We end up somewhere there. That's our second iterate. And again, we're going to hit this 45-degree line, and then we're just going to go away from that fixed point. I've given you guys an initial condition already on your plot. We'll go to that in a second. I just want to do one right here. And in this case, we will iterate away from x equals 0, and we'll leave that one there. What I want to do now is we're going to follow this initial condition that I already gave you. So it's going to come up here. It's going to go horizontal to the blue line and then vertically down. And then it's going to come along and intersect right there. And in this case, it's actually going to just oscillate between the 2 points.
So what's the significance of that? Is it like marginally stable, or is it like unstable?
We're going to get to that. It's a good question. So right now, both the fixed points are stable or unstable. And what we've just found now is a period 2 orbit. And we're going to look at the second iterate map, and we'll see that there are now actually 4 equilibrium points. 2 are unstable and 2 are stable. We're about to see that. So that's what happens when you have, bifurcations are very much related to the change in stability of fixed points in both vector fields and maps in general. And when you find, in this case, we had this transition. We started for alpha less than 1. We only had x equals 0 as being a fixed point. When we increased alpha, we had a bifurcation where xe equals 0 became unstable, and the other fixed point became stable. And then at alpha equals 3, we end up with another bifurcation where both of these fixed points become unstable. And as a result of that, a new set of fixed points is generated from the second iterative map, which we are about to see. We're about to go through some analysis, and then we'll look at the map of it, like an actual graph of it. One thing I want to add right here is that this guy right here is the period 2 orbit. So at alpha equals 3, this is the bifurcation point at which we suddenly get the emergence of a period 2 orbit. And this is called a period doubling bifurcation because the period doubled. All right, on the next page, like I just said, this stable period 2 orbit is generated, and we're going to compute that next. And to do that, we actually now need to solve xe is equal to g applied to g of xe. All right, so g of x is equal to alpha times g of x times 1 minus g of x, which is then equal to alpha times alpha x times 1 minus x multiplied by 1 minus alpha x 1 minus x. So to compute the second iterate map, we are substituting the function into itself and then expanding that. All right, so you can simplify that and get g of x is equal to x times alpha squared times 1 minus x times the quantity 1 minus alpha x plus alpha x squared. And then from here, we'll find that xe is equal to xe times alpha squared 1 minus xe times 1 minus alpha xe plus alpha xe squared. So again, we're not setting this equal to 0, we're setting it equal to xe, which is the key difference compared to a vector field. Okay, so you can solve this. We are not going to do it here. You can just use software or something to solve this. But what you end up finding is that xe can be equal to 0, which is what we had in the first iterate. And xe can also be equal to alpha minus 1 over alpha. Again, the fixed point from the first iterate. So by computing the fixed points of the second iterate, we also get the fixed points of the first. But if you don't compute them for the first, you wouldn't really know which are which. Okay, and we also get 2 more, which are much more complicated, and I guess the level of complexity is probably an indication as well. I have not computed the third iterate, so I don't know, or the fourth iterate as well. So, but I would imagine that the complexity goes up as well. So this is equal to 1 over 2 alpha squared times the quantity alpha plus alpha squared plus or minus alpha times the square root of minus 3 minus 2 alpha plus alpha, and all of that's under the square root. So like I said, the complexity went way up. Complexity in the sense of the number of terms, not in like the chaos theory of complexity. Okay, so in addition to the 2 original fixed points, we get 2 additional fixed points that show up in that third term. and that should be squared.
Yeah, okay. Oh, okay, that makes sense now.
Yeah, so the last alpha in the square root should be squared, because otherwise you would just reduce that down. Okay, so the two fixed points are complex whenever the quantity inside the square root is less than 0. So minus 3 minus 2 alpha plus alpha squared. This needs to be less than 0. And you can show then that minus 3 minus 2 alpha plus alpha squared is equal to 0 when alpha is equal to 3. Such that this is complex when alpha is less than 3. And then it's real when alpha is equal to or greater than 3. So when alpha is less than 3, we really only get two fixed points, the ones that we found in the first iterative. When we have alpha greater than or equal to 3, we suddenly get the emergence of these two additional fixed points, which are now real and stable. Okay, so here's what the second iterative map looks like with alpha being exactly 3. And in this case, it actually does intersect only at a single point. Over here, it only intersects at a single point. So if we take a look instead at alpha plus epsilon, where epsilon is a small parameter but greater than 0. In this case, I think it's 0.3 is what I used for this. In this case, and here I'm exaggerating, I chose a larger value of epsilon so that we could just see what's going on here without having to zoom in. But you can see now that we have xe equals 0 as that intersection, xe 1 and xe being the middle one right here, and xe 2. So to Mohammed's point here, we can now see that on the second iterative map, all of these are intersecting that 45-degree line. Whereas on the first iterative map, they weren't, because they were a period 2, not a period 1. Okay, and if you wanted, you could choose initial conditions on here and also study how these evolve as well. We're not going to do that. Okay, so this is known as a period doubling bifurcation. And if you were to plot the fixed points in the sense as a function of a state of what's going on versus alpha here, you end up finding that at 3 there is a bifurcation, and you get the splitting of that fixed point into 2 stable fixed points and 1 unstable fixed point. And then as you increase alpha, eventually the period 2 orbit loses stability, and it gives rise to a stable period 4 orbit, which then, as alpha increases, will eventually lose its stability and give rise to period 8, and then a period 16, and this goes all the way until infinity, and then chaos actually starts to emerge out of that as well. All right, so if we go to the next page, what you'll see is the bifurcation diagram for this system, for this map. So you can see on the x-axis we have alpha, which is our bifurcation parameter. For alpha less than 1, the only stable point is 0. So if we're thinking about population dynamics here, if that parameter was less than 1, then all the species would die out, or all the animals or whatever would die out and go to 0. If it's between 1 and 3, then they only have a stable single value for population. And if you're looking roughly between 3 and 3.5, there's now 2 periods. So you can imagine this in terms of population. In 1 year, we have a large population, and either there's not enough food for them, and so a lot die off, and then you have a lower population. Or maybe you could also expand this to predator-prey models as well. And the logistic map is not necessarily designed around predator-prey, but you can build things based on this as well. and eventually you end up with period 8 and so forth. All right, let's go to the second graph here, which is now a zoomed in view. Actually, hold on, I wanted to write some stuff here. So first we have stable period 1 orbits. Down here and also on that line moving up. We then get a stable, whoops. Let me move that to there too. And I'll lock it. All right. Hold on, I moved it off the page. Give me a moment. All right, we have stable period 1 orbit here and here. We have stable period 2 orbits on this branch and up here as well. Take a look at our zoomed in view here. We'll end up with that stable period 4 orbit. These guys. And right here, and then you can see after that we get a period 8, and then you'll get a 16 and 32, and then it progresses until you get a chaotic response.
What specifically does period 4, like, what does it mean? Other than there's, you know, you do a vertical line and it intersects 4 times.
So you know, we're picking some initial value for our population or whatever our system is. And over enough iterations, what will happen is it will jump between these 4 numbers. It will just cycle between them over and over. So in terms of like population dynamics, you're just going to cycle from too low to too high, basically. There are lots of applications of this stuff, and I have, as we move forward, I have one for like a hopping robot, I have one for milling machines, and then I also have one for chaos and a brushless DC motor, for a bifurcation diagram. We'll get there in a moment. Okay, so we're going to zoom in more here just so you can see in these solid black lines, the orbits are very dense, but you can start to see some kinds of gaps open. And one thing that if we go down to the bottom right here, in this zoomed in view right here, we end up with a stable period 3 orbit. Which I've always thought is fascinating because you're doubling the period and yet you end up with an odd number in terms of the period here. I've always found that fascinating. Because if you iterate infinitely, you always have some power of 2 due to the doubling. However, whenever you get a period 3 orbit, it is an indication that the system has become chaotic, in fact, actually. And in fact, there is a famous paper by Lee and York that is titled Period 3 Implies Chaos. And that's where they go and prove that when you have period 3 oscillations in these systems, they prove that it's a chaotic system at that point. MATLAB code for how I generated this bifurcation diagram is shown there on the right. You can see here I'm doing, in this case, 20,000 iterations, and then I'm just taking the last 1,000 iterations and plotting those. Because we do need to let the system settle. And I'm not entirely sure how long it takes to settle. You could do some math and compute that, but computers are powerful enough that you can just brute force your way now. Okay, So here's another example of a bifurcation diagram. This one was done for a hopping robot. This was actually done by my PhD advisor. He said this is the only paper he ever did anything on robotics. And in it, they produced this bifurcation diagram where they show it can evolve from period 1 to period 2, 4, and so forth. And then it evolves into having chaotic responses. On the next page, these come from a paper where they were studying bifurcation diagrams for a milling procedure, and they produced 2 bifurcation diagrams for different milling speeds here, 29,000 RPM, and then one for 30,000 RPM, and you can see how complicated and unique and interesting these things can get. And they actually do have real physical applications, is my point as well. The last example I'll show comes from studying controlling chaos in brushless DC motors, shown here, where they examine these different regions. And again, they have this period 2, period 4, and then the chaos appears as well, and period 3 as well. Okay. All right, we're going to do a little bit more instability analysis, and then given the time, we will start worksheet 3, and then we'll just finish it on Thursday. Okay, so for stability, the key thing is that the slope of the map at a fixed point must be less than or equal to 1, the magnitude of it at least. So we end up requiring that dg over dx evaluated at the fixed point. This must be less than or equal to 1. This is actually a concept very much related to flow K theory, where you compute flow K numbers, and if any of your flow K numbers have a real part greater than 1, you end up with instability. And when we were talking about the instability or unstable nonlinear normal modes, those are computed using flow K numbers and flow K theory. All right, so we're just going to do this for the quadratic map. We're going to start by computing the derivative dg over dx. And then this is simply alpha minus 2 alpha x, or you can write this as alpha times 1 minus 2x. Okay, so then we're going to take the magnitude of that, and this should be less than or equal to 1, and it's going to be equal to the magnitude of alpha. Hold on, let's add that we're evaluating here at x is equal to 0, and this is equal to alpha times 1 minus 2 times 0, which is equal to alpha, and therefore xe is stable, or xe equal to 0 is stable for alpha less than or equal to 1. For the second point, we can do that as well. In this case, we will have that the absolute value of dg dx evaluated x is equal to alpha minus 1 over alpha. This is equal to absolute value of alpha times 1 minus 2 times alpha minus 1 divided by alpha. Whoops. So value, which is equal to absolute value of alpha times fraction with the numerator of alpha minus 2 alpha plus 2 divided by alpha, absolute value. All that must be less than or equal to 1. You can eliminate this alpha and the alpha in the denominator, such that we find that the absolute value of alpha plus 2 must be less than or equal to 1, and therefore we find that xe equals to alpha minus 1 over alpha is stable for 1 less than or equal to alpha less than or equal to 3. Which matches the analysis we got graphically. Okay, so we can also compute the stability of the period 2 orbit of the map. In this case, we need to compute xe1 and xe2, which are then solutions of equation xe1, comma 2 equal to g of xe1, comma 2 alpha. We did this previously, and then from there, what we need to look at is that the absolute value of g squared, or the second iteration of g with respect to x, evaluated xe1 or 2, that must be less than or equal to 1. And we went through it in the notes. You're going to do this in worksheet 3 for the tent map.